These are some of the easiest DEs we saw of all semester. Some of the most fun. I really like these. However, these are also the ones that people get caught using Chegg for. Sometimes I don't notice on test one. Like there are going to be some people when I go through test one that I'm like, yeah, I suspect you a little bit. I'm going to keep an eye on you kind of thing. Test two is when people get caught. And it's on these kinds of problems. So I'm warning you now on test two, if you think you're going to use Chegg, I'm going to catch you. Okay, let's do these. So we got this second order linear, because I don't have any nonlinear versions of y. Homogeneous, because the right side equals 0, with constant coefficients. My coefficients here are just numbers. I don't have like this. That would still be linear because there's nothing nonlinear in y, but I would not have constant coefficients. My coefficient in front of y here is a 2x squared or a 3x. I don't even know how to solve this one. Okay, so this fits the pattern. It has everything we want. We assume a solution that looks like y equals e to the lambda. It doesn't tell me whether my independent variable was x or t, so I'm going to use x here. On the My Open Math homework, you got to be careful. Sometimes you're typing the answer and it'll tell you you're using the wrong variable. Usually the way you know what variable to use is it'll do something like this and it'll have the box. So you know you're supposed to be using t. Here, we're not told, so I'm just going to use x. Now, in the homework, I also have all those extra videos that you can watch. Some people, instead of lambda here, like to use an M or an R. You might see this written as that, or maybe this. That's perfectly fine. I see that a lot on the test. People will use M or R, and you get used to it by watching those extra videos. I'm used to that. That's not going to surprise me. So if you're one of those people that does that, I'm not going to look at that and get suspicious of you. However, I will always use lambda because that's the way I was taught. It's the way your book does it. So we assume the solution looks like this. Then y prime would be lambda e to the lambda x, and y double prime would be lambda squared. Sometimes my lambdas and my x's look too similar. Now we plug all of these into our differential equation. So that right there will be lambda squared e to the lambda x. I don't have a y prime in there. I just found y prime in order to find y double prime. I can factor out that common factor of e to the lambda x and get lambda squared minus 1. By the way, I want you to get to the point that you can go straight, at least in your brain, go straight from here to here. I want you to notice what we got here. That's a second derivative. I got a lambda squared. There's no derivative there. My coefficient is just a 1. I got a 1. Like you should be able to go straight from here to here once you do enough of these. In your brain, I still want you to write all this out. Okay, e to the lambda x never equals 0. So I'm allowed to just divide through by that and say, oh, well, lambda squared minus 1 must equal 0. That's a difference of squares, that's lambda minus 1, lambda plus 1 equals 0. We call this guy right here the characteristic polynomial. Sometimes you'll see it called the auxiliary equation. Auxiliary has two L's, I think. Those are two terms for this equation right here. I tend to use this one, characteristic polynomial. The solutions there are lambda equals -1 and 1. I assumed my solution was of this form. Now I've got two possibilities for what it could look like. That shouldn't surprise me. It's a second order differential equation. Second order DEs will have two linearly independent solutions. So that means y1, which is e to the 1x, and y2, e to the -1x or negative x, are both solutions. In fact, they're linearly independent solutions. If we were to calculate the Wronskian of those, we would find them to be linearly independent. And that's always going to happen. The solutions here, as long as you don't have repeated roots, as long as you have unique roots, you will always get a linearly independent set. Well, then from the theory of solutions, we have our general solution. Our general solution is the linear combination of these two. C1 e to the x plus C2 e to the negative x. If that were fourth order, we would have had 4 linearly independent solutions here. Okay, let's do another one. This one's going to cause a little trouble. By the way, again, I want you to be able to just look at this and go, okay, I'm going to get, so I know once I do all the work, I'm going to get lambda squared, because that's second order, minus 2 lambda to the first, because first order DE, plus, and then y will just be a lambda equals 0. This is what my characteristic polynomial is going to be. I'm just copying down the coefficients, 1, -2, 1, and then the order of the derivative, which end up translating into the power on lambda. I lied. I apologize. That's not a lambda. That's a 1. That's lambda to the first power because I have the first derivative. This is lambda to the 0 power because I have no derivative there. That's the 0 order derivative. That's what we're going to get. Let's see it. We assume y equals e to the lambda x. Then y prime will be lambda e to the lambda x. Y double prime, lambda squared, e to the lambda x. Throw all that in here. We get lambda squared, e to the lambda x, minus 2, lambda, y prime, plus the original, right here. Just a y right there. And that's supposed to equal 0. I have a common factor of e to the lambda x. And let's write down what's left. Lambda squared minus 2 lambda plus 1. It's exactly what I knew I was going to get. That guy never equals 0. So lambda squared minus 2 lambda plus 1 equals 0. There's my characteristic polynomial, also called the auxiliary equation. Okay, that factors, that's lambda minus 1 squared. That has a repeated root. I just get lambda equals 1 twice. I want to make sure that doesn't look like a negative. These are both lambda equals positive 1. Now, I could go through a whole bunch of math justifying this, but I already did in one of the theory videos. This means our two solutions, whenever you get a repeated root, your first one will just be e to the 1x. The second one, you got to tack on an extra x. If I had, say this were to the 5th power, so I had lambda equals 1 5 times, then my 5 linearly independent solutions would be e to the x, e to the lambda x. Oh, I know lambda's 1. X squared e to the x, x to the 3rd e to the x. They just keep tacking on extra x's until you build your entire set. These are linearly independent. We could check the Wronskian and see that. Like I have you do that in one assignment. We don't need to do that here. I'm telling you, once we've shown that, we don't have to keep showing it over and over again. These are linearly independent. So my general solution will be C1 times the first one plus C2 times the second one. Okay, and then one more example, and then we're done today. Same idea here. We're going to say, assume my solution is of the form u equals e to the lambda x. U prime, this is all going to be the same, right? U double prime, lambda squared, e to the lambda x, plug everybody in. X minus 2 times the derivative plus 4 times the original equals 0. Factor out that e to the lambda x. We're going to get lambda squared minus 2 lambda plus 4. So look, my characteristic polynomial was sitting right in front of me. It's going to be 1, -2, 4, and it's a quadratic. That's going to happen every single time. That's what I'm saying. I want you to be able to just look at that and go, yeah, okay, that's right. We get this equation. This guy's not going to factor. In fact, we're going to get complex roots here. So we need to solve this equation, quadratic formula, completing the square, however you want to do it. I find it quicker to use completing the square. So that's how I'm going to do this, because honestly, I don't remember what the answers were. But if you want to use quadratic formula, that's perfectly fine. I would do lambda 2 lambda plus blank equals -4 plus blank. Half of 2 is 1, squared is 1. I'm going to add 1 into both sides. Then the left-hand side is a perfect square trinomial, and we'll factor lambda minus half of that guy squared. Over here, we get -3. Take square root of both sides. Don't forget our plus or minus. I get lambda minus 1 is plus or minus I times √3. So lambda will be 1 plus or minus I √3. We have complex solutions. And again, I could go through all the math behind the magic that's about to happen, but I'm not going to because I've already done it in one of the theory videos. If you get complex solutions, if lambda is a plus or minus bi, then your solutions are y equals e to the ax cosine of bx, and y2 is e to the ax sine of bx. And that's using Euler's formula and going through a whole bunch of math that you don't need to go through every single time. You just plug in like this. So my A is 1, my B is square root of 3. The I just tells us that I need this form. There won't be an I in my answer. So then my solutions here will be e to the x cosine of square root of 3x, and y2 is e to the 1x, e to the x sine root 3x. And then the general solution is just the linear combination of these two, y equals c1. I'm literally just writing all this down now. Sine of root 3x. All right, any questions?